questions.
Okay.
So next time if you could just like address
Sure.
one.
Yeah. So we have another 10-minute talk coming up. So the talk is by Hyun-Min Joe, who's from KAIST. So you have 10 minutes and then 5 minutes for questions.
Good afternoon. My name is Hyun-Min Joe, and I'm a PhD student in KAIST Hubo. My research topic is design and implementation of balance controller for stable walking on uneven terrain. So research objective is to develop a balance controller for stable locomotion of humanoid robots in general environment without terrain information. The DR Plus used in the experiment was developed to perform tasks in a disaster environment. The height and weight are 1.7 meter and 8 kilogram respectively. Electric motor is used as the actuator, and the IMU for estimating the COM state and the FT sensor for measuring the ground reaction force are mounted on the pelvis and feet respectively. And the rubber is attached to the soles to reduce impact force when the foot lands on ground. To copy the disturbance from the various environments, the contact force between feet and floor must be controlled. There are three strategies in biped walking control. The first one is ankle strategy, and second one is hip strategy, and third one is stepping strategy. Hubo has a relatively large foot, and the DR Hubo has a slow, foot speed is slow, and the upper body is used to perform some task. So considering these conditions, we have designed the balance control that makes the most of the anchor strategy. First, I will explain the overall control architecture, and then I will explain each component from the following. The contact force reference is calculated from the desired GMP, which is generated by capture point control. The center of mass trajectory and the foot trajectory that follow the desired GMP are generated in the pattern generator, while the stabilizer adjusts the position and orientation of the foot and the COM position for disturbance rejection. We use the model pref control to calculate the optimal COM and the foot trajectory to follow the desired GMP at the same time while taking account the size of foot and the range in which the foot can move. The below video shows the result of simulation when the disturbance is applied between 0.6 meter and 1.6 meter in the X direction when the robot is walking at a constant speed in X direction. Notice that the red line output GMP is maintained in the black rectangle representing the foot while adjusting the step position. Yes, since the size of foot is taken into account in pattern generator. And stabilizer designed for disturbance rejection has three control components. Stabilizer has a horizontal component that adjusts the COM in horizontal direction, and the vertical component that adjusts the foot position in vertical direction, and the rotational component that adjusts the orientation of foot. The horizontal component regulates the zero moment point through acceleration of a center of mass in the horizontal direction. The DR Hubo is a rightly damped system as shown in the left video. Because these oscillations cause instability when walking, we have designed the steady feedback controller to increase the damping of the system, suppressing the vibration, like as shown in the right video. The vertical component adjusts the vertical position of the feet in order to adapt to the terrain elevation, like as shown in the video on the right. The desired vertical force of each foot, calculated from the desired GMP, is tracked through the foot position control. The foot position control input for vertical direction is determined by the the PT control to follow the desired vertical force. And the rotational component control the orientation of the foot to adapt the slope of ground as shown in the video. The orientation of foot is adjusted to follow the desired foot torque calculated from the desired GMP. As shown in the video, I adjusted the slope to test the stabilizer, and you can see that the robot maintains the balance through these designed stabilizers. Using the designed working pattern and the stabilizer, we tested the performance of designed balance control on various grounds. This experiment video shows that the robot walks up on a 10-degree slope without terrain information. This video shows that the robot is walking on a locally inclined ground. Through the designed balance controller, the robot can walk stably on locally inclined terrain. We also tested the balance controller on the road. We confirmed that the robot can move stably, like as shown in video. This video shows that when a large disturbance, which cannot be controlled by ankle torque, is applied, the robot adjusts the position of foot to maintain balance. Okay, conclusion. Based on the capture point control, working pattern and stabilizer are designed so that the robot can walk stably on an uneven terrain. When large disturbance, which exceeds the contact force limit, is applied to the robot changes the step position to move support polygon. Okay, thank you.
So we have some time for questions, and also just a reminder, we have the Slack channel in case people want to give questions over Slack, and we have a Slack monitor that's moderating that part. So any questions or comments?
Thank you. I was wondering, in the last video you have, so you put a wooden, a wooden bar on the robot foot, and the robot adapts its orientation of the feet, but it kind of conserves it for like maybe a step or step and a half. Is it like included into the controller or is it just due to the compliance that is a bit delayed, or?
In this video, the robot used the anchor strategy and stepping strategy simultaneously. So he adapts the he adjusts the orientation of foot, and then but he cannot recover the balance. So he changed step position. Yeah, because there is the robot has a finite size of foot, so the desired GMP calculated by capture point control is exceeded the support polygon. So the robot changed the step position.
Okay, thank you.
Yeah.
Any other questions from people? I guess I have one question. So we just saw Jerry's talk where he's talking about stepping down from unexpected heights. How would your robot adapt if it was stepping down from a height that was unexpected?
In our robot, he can adapt to the 10 centimeter height difference. Yeah. So I think when we design the controller, the control bandwidth is important. Yeah. So we try to increase the control bandwidth. Yeah.
And so have you tested it stepping down from different heights? So you show kind of different types of perturbations on uneven terrain.
Yeah.
Have you shown where it just is stepping off a step or down onto a platform?
Yeah. So yeah, he changed the he controlled the leg lengths.
The leg length?
Yeah, leg lengths.
Okay.
Yeah.
Yep. Any other questions from anybody else? Were there any questions on Slack?
No, there's not.
Okay, so let's thank Hyun-Min again for his talk.